First of all, it's important to say that all instruments and devices currently on my workbench were purchased by me. Nothing was donated or loaned by any manufacturer or representative, except for a few small, older devices that were given to me or traded with friends. Full microwave generators are normally very expensive and many times beyond the budget of the average microwave experimenter. This 40 GHz model from Siglent, for example, probably will cost about $58,000 US. Fortunately, there are more affordable devices on the market with interesting features that could enrich your workbench. Normally, they won't have modulation facilities. Some will have just pulse modulation, but some will have decent spectrum purity, good output attenuation control, and nice phase noise figures. In this video, I will make a review of the DS30000PRO low noise microwave signal generator, produced by a small American company, DS Instruments, using the resources I have available in my humble lab. Here is the back panel of the SG30000A. Sometimes DS Instruments releases new hardware revisions. Mine is revision R10 and the output connector is 2.92 millimeters. As many times I don't need high output levels, I normally use a 10 dB attenuator at the output, helping to protect the output amplifier from mistakes. This model has a premium internal reference source that can be locked to an external 10 or 100 MHz source. These holes in the enclosure are air outlets for the forced air cooling system, which, by the way, is turned on and off depending on the internal temperature, saving you from continuous acoustic noise. As we will see in a while, the generator can be controlled remotely via the USB or Ethernet port, or standalone with reduced capacity. There are two USB-C connectors, one for just extra power and the other for power and data. The total current can reach up to 1.75 amps. On the front panel we have a small display, an external trigger connector, 3 control buttons and 3 LEDs. Status, oven temperature status when using the internal reference, and RF on off. There are also 4 air inlet holes. When using in the standalone mode, the display will show a circular menu, and each time you press the mode button, it will show a different parameter. The arrow buttons will change the setting of a particular parameter. This is the control window you will normally use when you connect your laptop to the generator via the USB port. Pressing the search button, the software will check the available COM ports in your laptop. Search. and connect will establish the connection. Here you can choose the reference frequency scheme. For this demo, I'm now using an external 10 MHz reference. Here is the internal voltage. Be sure to have a voltage within the USB standard limits. And here is the internal temperature. A small fan will start to blow when the temperature is too high. Adjust the frequency step and output frequency here. The same for the output level. This offset field is very convenient. For instance, I normally have a 10 dB attenuator connected to the output. Then when I set this parameter to minus 10, the output level will be corrected. This is not available in the standalone mode. Let's try here 1 GHz. And level step 1 dB. With the vernier slide button, you can make a fine adjustment of the power output with steps of about 0.05 dB. This is very convenient, but be aware that when you use this function, the generator will enter in an uncalibrated mode because there will be no feedback from the amplifiers to let the device know the exact power level at the current frequency. On the other hand, the uncalibrated mode can give you about 2 more dB of power than the maximum level specified, in this case plus 15 dBm, and about 10 dB less than the minimum. But this will depend on the frequency range you are. This section here allows to introduce a phase shift to the waveform. I will test this feature later on in the video. And finally, with these buttons here, you can turn the power on and or off. The generator can also be controlled remotely using the Ethernet port and the same application we just used. In both the USB and Ethernet modes, we can also send a command using this field here. For instance, let's disable the buzzer. Buzzer off, send command. Buzzer on, and command. Now let's check the performance of the SG30000PRO, starting with the output level accuracy. The first method used was the power meter, and I used this trustworthy NRP Z221 average power sensor made by Schwarz. Notice that this is a device for 10 MHz to 18 GHz range, but the interesting thing is that its sensors respond up to 30 GHz. Notice also that there is a 10 dB attenuator at the generator output, and this certainly helps to keep the input impedance closer to 50 ohms. If we ignore this point here, this is 29 GHz, the whole range error is below 1 dBm. Well, of course above 18 GHz the measurements are not reliable, because I didn't have yet the opportunity to calibrate the sensor in that range. Next, I will make the same measurements with the spectral analyzer and try to compare. Here are the results. They are not much different from the previous measurements using the power meter. The variation in general is about 0.2 to 0.8 dBm up to 18 gigahertz, which is the frequency limit of my spectral analyzer. I have included just one frequency above 18 gigahertz, based on the measurement I made using a 40 gigahertz mixer, the ZMDB44HK from mini circuits. The reason is that I found in the mixer specs that with a 25 gigahertz at the RF port and with 15 gigahertz plus 15 dBm at the local oscillator port, the conversion loss of the mixer is 10.1 dB. Let's see here. RF port 25 gigahertz, LO port 15 gigahertz plus 15 dBm. The conversion loss is 10.1 dB. Then with this setup here, the measured power is about minus 22.3 dBm. Considering also the losses in the cable and adapters, the real power is minus 10.5 dBm or 0.5 dBm below the nominal power. Concluding with the power meter, I found that the difference between the minimum and maximum levels is 1.6 dBm, and with the spectral analyzer is 1.7 dBm, and the typical variation declared in the generator specs here is plus minus 1 dBm or 2 dBm variation. And here we can see the quality of the signal generated. Notice that there's a 10 dB attenuator at the generator output, so the real level of the generator is 0 dBm. The filtered ranges start with 300 megahertz, and I measured up to 36 gigahertz the second and third harmonics. Above 18 gigahertz I had to use the mixer, so the numbers are estimated. I assumed 12 dB as the mixer conversion loss. Practically all results are below the typical values specified, which are minus 30 dBc for filtered bands and minus 12 for unfiltered bands. In this line we have the final numbers, and the cable and adapter losses were accounted for. I didn't find anything in the specs about artifacts or spurs in the generator range, so I inspected the generator output, chasing spurs, artifacts and subharmonics. It's impossible in a short video like this one to explore all the possibilities, so we will take some frequencies as example. For integer frequencies within 1 megahertz steps, the spectrum is very clean, normally up to minus 70 dBc, like this one here. Let's choose other frequencies. 9 gigahertz. The same. 1.17 gigahertz. Well, you can see that for lower frequencies it's even better, minus 80 dBc. Next, let's look for subharmonics and then talk about integer boundary spurs. Subharmonics many times is a result of leakage in a multiplier, doubler, quadrupler, etc. And boundary spurs are inherent to fractional synthesizers, and they appear in the proximity of an integer frequency. There are special software programming techniques to minimize this effect. Now let's chase some subharmonics. I set 28 gigahertz carrier 0 dBm, and the spectral analyzer is tuned to 14 gigahertz. We can see that we have here minus 43 dBm, which is okay. Now let's change the frequency to 1/3 of the carrier. It's nothing here. And now 1/4, 7 gigahertz. And 7 gigahertz, there is nothing. Now let's change the frequency to 4.5 gigahertz, 2.25 gigahertz, nothing, 1.5 gigahertz. We set now 20 gigahertz. Look for subharmonic 10 gigahertz. Well, for 10 gigahertz we have minus 30 dBm. So now let's try 18 gigahertz and have a look at 9 gigahertz, minus 43. Now let's have a look at boundary spurs. As I said before, for 1 megahertz steps, everything appears just fine, but for smaller steps, we will have to live with more spurs. For lower frequencies, it's a bit better. Let's start with 100 kilohertz step and a 18 gigahertz carrier. 0.1 megahertz. And you see here that the spurs are 10, 20, 30, more than 30 dBc below the carrier. 3 gigahertz. 0.1 megahertz step. Here we go. A bit better. 10, 20, 30, 40, below minus 40 dBc. One more, 1 gigahertz. 0.1 step. It's better. Let's try 0.01 step. Okay, for lower frequencies, the step can be a little bit smaller, 10 kilohertz maybe. Here we see 10, 20, 30, 40, 40 something. The great picture of the attenuation engine is shown in this spreadsheet, and it's not bad at all. The DS instruments Spartan specifications show that for frequencies below 6 gigahertz, the maximum step attenuation allowed is 60 dB, and above this frequency is 31 dB. But in fact, it's better than that. It shows up to 23 gigahertz here, but it's probably a typo. Notice that there is a 10 dB attenuator at the generator output, so 0 dB attenuation corresponds to plus 5 dBm level at the output of the attenuator, or plus 15 dBm level at the output of the generator, which is the maximum level specified. This row here, relative error, shows the error in relation to the 0 dB level measured. The second row, absolute error, shows the 0 dB level error in relation to the nominal level, which is plus 5 dBm. The third rule is the accumulated error or total error, which is in all frequencies measured inside the plus minus 1 dBm typical error specified by DS instruments. Here. Again, for frequencies below 18 GHz, I use the spectrum analyzer. If for frequencies above 18 GHz, the power meter in extended range. Reason why I left this note here, not reliable. Phase noise is certainly one of the most important quality indicators of a microwave generator. DS Instruments specifies phase noise for three frequencies, 6, 12 and 18 GHz at 10 kHz offset, but unfortunately at this moment I can only measure the phase noise of a 6 GHz carrier. Here is my setup to do that. This device will measure the phase noise using the cross correlation mode. Here we have two very clean 100 MHz references with only minus 100 dBc per hertz phase noise at a 10 Hz offset. This is a 6 GHz active mixer, and this a 6.05 GHz local oscillator, so to have 50 MHz at the output. Let's see the results. Here we can see that for 10 kHz offset we have minus 106.5 dBc per hertz, or more than 10 dB better than the specification. At 100 Hz we have minus 91.7, and at 10 Hz we have minus 64.9. Very good. I decide to make another measurement now for a 2 GHz carrier. Let's see what happens. Okay, so we have for an offset of 10 kHz, we have minus 116 dBc per hertz. For 1 kHz, minus 101. For 10, about 71 dBc per hertz. Not bad. I said before that with this section here I could shift the output waveform. We have now 0 degrees. The test frequency is 400 MHz. Wavelength is 2.5 nanoseconds. And here the yellow sinusoid comes from this generator, which is locked to my high stability frequency reference. So the yellow sinusoid will be the reference for this measurement. So go back to the green sinusoid is also 400 megahertz, coming from the DS instruments generator, which is also locked to my high stability reference. I took 2 points here, one in the yellow waveform and the other in the green waveform, and this distance is 4 nanoseconds. Now I will shift the output 100 degrees. Let me show what's 40. Let me show what's happening in the scope. Remember that the wavelength of 400 megahertz signal is 2.5 nanoseconds or 360 degrees. So 100 degrees will correspond to 0.94 nanoseconds. Let's approximate to 0.7 nanoseconds. This means that the difference between 4 nanoseconds and the new measurement has to be approximately 0.7 nanoseconds. Oh, let's check that. .3 nanoseconds. 4 nanoseconds minus 3.3 nanoseconds is 0.7 nanoseconds, as expected. The phase shift function is available for frequencies greater than 150 megahertz. In the specification, we see that the typical frequency step size is 2 Hz here, which is good. And now we're gonna check that. My microwave frequency counter goes only up to 15 gigahertz. So I have to include a mixer to bring down the frequency, and here is the setup. Here we have the mixer, the 15 gigahertz local oscillator, amplifier, this is a level 15 mixer, and here another amplifier for the counter. I will start measuring 29 gigahertz, which is very close to the generator maximum frequency. Minus 15 gigahertz, 14 gigahertz. This last digit here is 0.1 hertz. Now I will add 1 hertz. Nothing happened there. Now 2 hertz. Okay, 2 hertz. Now let's try 17 gigahertz. (17 minus 15) 2 gigahertz. Let's add 1 hertz. Nothing happened. 2 hertz. Okay, 2 hertz. Let me reduce 1 digit here. Now let's try 15 gigahertz. I will remove this setup and connect the generator directly to the counter. Okay, 15 gigahertz. I'm gonna add 1 hertz. Nothing happened there. 1 more. And 2 hertz. Now I will decrease 1 hertz And here we go, 1 Hertz. So below 15 gigahertz the step is 1 Hertz, and above 15 gigahertz 2 Hertz, meaning that probably there is a doubler for frequencies above 15 gigahertz. Now let's try 2 more frequencies. First 1.2 gigahertz. .2 gigahertz. Let me reduce 1 digit and add 1 Hertz. Now the last frequency, 275 megahertz. Well, I will have to change the input of the counter. Okay, 275 gigahertz. Let's add 1 Hertz. Hertz. The generator can sweep as well, and there's another piece of software to do that. There are 2 modes, scan and list. In the scan mode, you give the start frequency, stop frequency, number of points, dwell time. You specify if the sweep is single or continuous, if the direction is up or down, and so on. And in the list mode is basically the same, but you give a list of frequencies here. Let's try to make a sweep here. I informed start frequency 5 gigahertz, stop 8 gigahertz, dwell time 350 milliseconds, and 10 points. A single sweep, the up direction. Now I send settings and trigger sweep. And you can see here again. Trigger sweep. In the list mode, I tried before and it's not working. You have to check with DS instrument what's happening. Probably I don't have the correct release of the software. But you just insert the frequencies here and it will do the same. By the way, the generator won't take much space on your workbench. It has been more than 2 years since I bought this generator, and I must say that I didn't use it intensively, but when needed, it always performed as expected. It's simple to use, don't take much space, and as you saw in the tests, the quality is good. Accurate attenuators, very clean output for 1 MHz steps, great range, level stability, and has power enough to drive a level 15 mixer. The maximum attenuation is very good and it can always be improved, especially at the end of the range with extra precise attenuators. It doesn't have modulation or fancy capabilities, and you will have to live with more spurs for smaller steps, but this is reflected on its low price. My unit is an anterior version, so may be a bit different from the one they are selling now. Of course, I don't have a metrology or certification lab, and I don't take my instruments regularly to the manufacturer to be calibrated, and to cover all the details I would take much more time and hundreds of thousands of dollars worth instruments. There are some details that I probably missed, but I'm sure you will point them out in the comments below. I contacted DS Instruments just a couple of times since I bought it, and the people there were friendly and helpful. They also have many other products, especially other microwave generators that may be worth having a look at. Well, that's all I had. Thanks for watching.